So some of you asked me about lecture notes. So this has already been mentioned, but relatively recently, I wrote down together with some of my long-term collaborators a pretty long review on string cosmology. The title is String Cosmology from the Early Universe to Today. So you can have a look at that. There is a whole introduction on standard cosmology, compactifications, and then applications to inflationary heating, dark matter, dark radiation, dark energy, and also applications to scenarios which are different from the standard ones. So like ekpyrotic and so on. So please have a look at that. So we were basically trying to see an explicit model where inflation is realized by a Kähler modulus. Remember? The Kähler modulus that had to be orthogonal to the overall volume. And that was the introduction. So these were different scenarios. We got up to this point. So where the Calabi-Yau looks like that's the volume of the Calabi-Yau. Remember, the taus are 4-cycle volumes. So this is the typical Swiss cheese model. So there's the pictorial view where you have a big cycle, tau big, that controls the volume. And then you have tau phi and tau s, which are like holes in this Swiss cheese that are blow-ups of point-like singularities. So then you see that the volume can be approximated as tau big to the 3/2. Then we've seen that when you add alpha prime corrections, alpha prime cubed corrections, as well as non-perturbative corrections for tau phi and tau s, you generate a potential that at leading order stabilizes the volume, which is exponentially large in terms of tau s at leading order, and it stabilizes tau s as well as 1/G string. On top of that, I didn't write it down here, but secretly, this introduces also dependence on theta for s, right? Because here, this is dependence on Ts. There is tau s plus I theta s. So there will be a dependence here, which is a cosine of, in this case, as theta s. And this minimization gives me the minus sign. So at this point, here, out of the 6 fields that I have, so 3 taus and 3 thetas, at this point, I stabilize 3 of them. So I stabilize the volume, theta s and tau s. So then I'm left over with other fields. So at this point, when I add these non-perturbative corrections for T phi, I generate a potential for tau phi and theta phi. So this minus sign is again from the stabilization of theta phi. It's a cosine that becomes -1. And that is the subleading order potential for the inflaton. And by the way, there is a last field, which is the axion associated to the big cycle. So that one will be stabilized by another non-perturbative effect, which will go like e to the minus t big. But I'm ignoring it because the volume is exponentially large. So this would be super suppressed. So it's basically a very light field that is around. So there will be an even further contribution with this very light field. So that's not important for inflation, okay, because it's just a spectator field. So basically you are inflating, in this case, around this potential. So you go down, and your orthogonal direction, you have this axion that is very light. Okay, so it's like a spectator field. But that's very important for the post-inflationary evolution, because you have that at the end of inflation, the inflaton decays, and it can decay to this very light guy. And this very light guy, given that it is basically massless, behaves as radiation. And this is dark radiation that is very generic in these models and contributes to the effective number of neutrino-like species that you have in the universe that is constrained by data. So that's a very important observable. So up to this point, we have... oops. What happened? It doesn't work anymore. Okay.
Then change the file is corrupted with a logo. The tools.
No, now I don't know why there are two white pages, but that's fine. It's fine. So remember that then we looked at loop corrections. So we started writing. Let me make it full screen. So we started looking at good the expression of these corrections, and we mentioned their generalization to a Calabi-Yau. Is it working now? Yes. So now let me give you a kind of effective theory interpretation you might be more familiar with for these loop corrections. So basically, one is that these are corrections to the Kähler potential, and we've seen that the Kähler potential gives the kinetic terms. So if you have a loop correction to the Kähler potential, this should lead to corrections to the kinetic terms, as well as corrections to the potential. Because remember, the potential is also contribution from the Kähler potential. So one can give a low energy field theory interpretation, at least for these corrections that are seen as heavy modes running in the loop. So this is a very simple argument. So let's say that you have a heavy mode H coupled to a light mode L. So you have the mass for the heavy mode, and then there is a coupling light, heavy squared with some strength G. So that gives rise to this kind of loop correction to the 2-point function for L. And from the 2-point function, one loop renormalization, you know that the kinetic terms get this correction that goes like G over M squared, with a loop factor that is typically of order 1/16 pi squared. Now, let's say that we are in a string theory setup, and L for us is one of the moduli, one of the light fields. For example, it could be the volume mode. And now I want to compute its coupling to a heavy field that runs in the loop. So this can be like a K mode, a string state, winding state, whatever. So one can do the following. So the mass of, as we've seen, the Kaluza-Klein mass is a function of the volume. So it's a function of the tau. What I can do, I can expand tau around the minimum. So I can write it down. Basically, what I'm doing here, I'm writing tau as some, so this tau is a function of x. So some vacuum expectation value that I find by minimizing the potential. So that will be the minimum. And then I expand the theory around the minimum. So there will be some tau hat of x. And given that the mass is a function of tau, I can expand. Then I get m, which is just the situation where tau is at the minimum. Then I get the first derivative times tau hat h squared. And basically, this thing is power law. So I get tau hat divided by the variable tau. And then what I should do to get the coupling between the light and the heavy state is to canonically normalize this guy, because this is not canonically normalized. And remember, we've seen that K is minus 2 log of the volume. But we are in a situation where now we are considering tau big for this tau. So the volume, we've seen that goes like tau to the 3/2 in the case of tau big. So now I can write this down as minus 3 log of tau, right? When I write down tau to 3/2. And then when you look at the kinetic terms, remember they were the second derivative of K, basically with respect to tau squared with some coefficient. Now it doesn't matter, it's 1/4. You have d mu tau, right? So this is pretty simple. So when you do the second derivative, you will get something that goes like 1/tau squared, d mu tau, with some coefficient. I don't care. Now what I want to do, I want to canonically normalize these around this point, right? Because I'm considering small fluctuations around the vacuum. So I can do the expansion. Here I consider the vacuum. And here I'm left over with tau hat, which is a function of x. And then I want to write this down as 1/2 d mu L, right? The standard kinetic terms. That's easy. So that tells you that basically tau hat divided by the vacuum expectation value of tau goes like L now of x. And these are all dimensionless, because now it's important to plug back units of Planck. I want to give to this the standard unit of mass unit of a scalar field, which is a mass. Then I divide to get something that is dimensionless by the Planck mass. So basically, this is what I'm doing here. This is where it comes from. So then you can see that I get this coupling, GL h squared, where G is the mass squared of this heavy mode running in the loop divided by M Planck. Then I use this standard quantum field theory formula. I get C loop M divided by M Planck squared. Then I can expand. I can write this kinetic term. I just did it at the blackboard in this way. And then I know that this whole thing, given that it gives me the kinetic term, should be the second derivative of the Killer potential plus the correction with the second derivative. I can then infer that a leading order, I get 1 of tau squared, as we've seen, from 3 level. And then this correction should go like, with the second derivative, C loop over tau squared, M over M Planck squared. Then I can integrate back twice, and I get that the 3 level is minus 3 log of tau, whereas this loop correction should go like C loop M divided by M Planck squared. And then it depends on what kind of field is running in the loop, because that tells you what the mass should be. And so we tried, so that's the formula that we inferred from effective field theory. Now let's say that H, so the heavy field is a string state, so it's a massive string state. Then you can write M as the string scale. We've seen yesterday that is M Planck divided by square root of the volume. Then here you get 1 over the volume, so C loop over the volume. And this is nice because it matches the computation done by these people for the alpha prime corrections. And this makes sense because this should be this correction should be related to the integrating out stringy states. So that's good. This interpretation makes sense. There is no dependence on the inflaton, so that's not important for inflation. So for understanding how the potential for the inflaton looks like. Now, when is a winding mode? Instead, winding modes M winding have a mass, which is the string scale times a length, right? Because it is a winding state. Now, we care about the dependence on the Kira moduli. So remember, the tau is a 4th cycle modulus, so it's a length to the 4th. So then we need to take the 1/4 power. You need to write down everything in terms of M Planck because you're in supergravity. So you need to rewrite and string in terms of M Planck, and you work out that this correction should go like square root of tau divided by the volume, and this matches exactly the scaling of the corrections that Bergach and Peyer called KK, because from their point of view, this was a 3-level exchange of Kaluza-Klein strings, closed strings, and these can be interpreted somehow as one loop of winding strings. However, we've seen that this correction that now might depend on the inflaton, they enjoy an extending no-scale structure cancellation. So their contribution that I mentioned this morning to the potential again becomes irrelevant because it is 0, a leading order. The important one is instead the situation when I have Kaluza-Klein states. Now I substitute the Kaluza-Klein scale, I get M string now divided by a length. So tau to the 1/4, I play the same game, and I get C loop divided by the volume times square root of tau. And this matches again the scaling of Bergach and Peyer for these winding corrections. And the reason is that in this case, they were looking at the exchange at 3 level of winding closed strings. Maybe this is my sound a bit too abstract, maybe let me try with a picture just to give you an idea. So I don't know if this works or not, but somehow you had these two D7 brains, let's say, that were intersecting over, in this case, a 2 cycle. Now I cannot draw it, but I can draw just 1 cycle. And then there were these loops that were interpreted as basically the 3-level exchange. So there could be strings that are closed strings now that are winding around this cycle, the intersection, and they are exchanged. Now, basically, our interpretation instead was in terms of MKK. So it means that there should be some Kaluza-Klein states that are now running in the loop, and these are open strings. So basically, open strings that are here at the intersection, and basically they go around the loop here. But then you see that you have the same diagram as the exchange of a winding closed string intuitively. And then we get this kind of correction. And this would be the correction that now is relevant for inflation. So it's a correction that goes like a loop coefficient divided by volume cube, and then square root of tau phi. That would be the inflaton. So that's crucial for inflation. Now, we were not super happy with just this interpretation. So we tried also to give another interpretation from low energy in terms of the potential. Because I said that the corrections to the Kähler potential give correction to the kinetic terms, but also to the scalar potential. And we know that the scalar potential receives one loop corrections that take the Kollmann-Weinberg expression. So here there's the cutoff of the effective field theory and the super trace of the mass squared matrix. And now what we want to do, we want to rewrite this down in terms of the moduli to see if we get a scaling that matches with what we've seen before. And we did that in the following way. So the super trace of m squared is the gravitino mass squared, is a result, known result in supergravity. And we've seen that the gravitino mass can be written down in terms of the volume. So the gravitino mass squared is one of the volume squared. And then you need to look at lambda. Lambda is the cutoff of your effective field theory. And this is given by the Kaluza-Klein scale associated to open strings on D7 brains. So then you can try, when you put the D7s on tau big, so this would be like D7 brains wrapping tau big, you can write down the Kaluza-Klein scale. And then you infer that the loop, the correction to the scalar potential goes like 1 of volume to the 3rd, with no dependence on tau phi. And this is not relevant for inflation. Again, it's just a small correction. But when you have the 7 brains wrapping tau phi, now the Kaluza-Klein scale depends on tau phi. You can plug it back there, and you see you get the same expression, 1 over volume cubed square root of tau phi, that we got from this 2-point function interpretation. So we were pretty happy with that. And by the way, let me stress the fact that in the Kollmann-Weinberg potential, there is a leading contribution that goes like cutoff to the 4th. Okay, so there is cutoff to the 4th, and then there is a cutoff squared. The piece with cutoff to the 4th, if you try to play this game, would be leading. However, the coefficient of that is the super trace of M0, which is basically a number of bosons minus the number of fermions in the theory. And given that this theory is supersymmetric, this coefficient is 0. And somehow we managed also to understand this extended no-scale cancellation that we found in the equations by performing a matching with the first term that they didn't write down. That is also a cancellation. So maybe that is due to supersymmetry. Now, one more thing that we thought about was that, well, what about if there is no D7 brain wrapping this guy? So could it be that these corrections are not there? Well, still there will be no open string loop corrections, but you could still have closed string loop corrections. And where now in the loop, you have the KK modes of this closed string itself. This can be there. And these are expected also to be localized around this block mode. And again, you compute the cutoff lambda as the same form, and you get again the same dependence. So somehow it seems that these loop corrections are really unavoidable, and you need to include them. So let's see. Let's now go to some phenomenologies and cosmology. So now the total potential should look like this. So this is the constant piece, the V0. Remember, that depends just on the volume. These are, sorry for coming there. So these two terms are the non-perturbative effects that were introduced before. And now these are the loop corrections that we wrote down using this conjecture from Bergach Empire, coming from explicit toroidal computations, and also using our low energy field theory interpretation. And now basically, this is the form of the potential along tau phi. You see the yellow line is when there are no loops. So you kill them. And this was the original model of Conlon and Quevedo, where basically when you are at the minimum, these terms are important. But then when you move tau phi away from the minimum, you see these become exponentially suppressed. So very quickly they go to zero. This was not there. You remain with this term. The volume has been fixed, the leading order, and this gives you this plateau. And that is the way how they realized inflation. But then we found that basically now when you add these loop corrections close to the minimum, remember these guys were going like 1 over volume cubed, 1 over volume cubed, because the volume was exponentially large and was balancing, they were balancing against that. So close to the minimum, this guy goes like 1 over volume cubed, but then there is also loop factor and also square root of tau phi. Tau phi needs also to be a bit big to trust the supergravity approximation. So close to the minimum, you can ignore it. So the minimum is still the same. But then when you start moving away from the minimum, you see these two guys go to zero very quickly because they are exponentially suppressed. So at a certain point in this region where Conlon and Quevedo were inflating, this guy dominates, and because it is only power law suppressed, and actually ruins inflation. However, if you go to even farther feed ranges, this guy is also suppressed, right? When you go to large tau phi. So you should find a regime where this term dominates, and you should be able to reobtain inflation. The only worry that we had in the past, and that's the reason why we didn't write down this theory, was that here we're basically keeping the volume fixed, and we are taking tau phi very large. So pictorially, what it means is that we keep the volume fixed, but this guy becomes very large, right? So you are in a situation where at the beginning of inflation, this is big, geometrically, this whole, and then it becomes small. However, it could be that at a certain point, to reach the plateau region where the potential is flat enough, you need to go to very large values of tau phi, and then you could be in a situation where this hole is as big as the big cycle, right? And that could be a situation where you start having problems. So you don't trust the effective theory anymore. You see also this cannot be the case because you have that the volume is, as we've seen, tau big to the 3/2 minus tau small to the 3/2 minus tau phi to the 3/2. You cannot get a negative volume. And so you cannot have tau phi that is too big. However, we checked that it works. This is not the case. And actually we checked that in order to reobtain the original model of non-perturbative block inflation, this correction of the loops should be tiny, really tiny, which is not what we expect. We expect to be something like 1 over 16 pi squared, just 10 to minus 2, maybe 10 to minus 3, but not like that. So for C loop, which is bigger then 10 to minus 6. When I go away from the minimum, the potential here that now becomes, for example, the dashed green one, where C loop has to be positive, because if C loop is negative, then this goes down and doesn't work. Now, in this case, you see it gets tilted a bit, and I can ignore these two contributions, and I just get that the potential is this constant piece plus that. Then I do the canonical normalization, as I did here. So here I did the canonical normalization for this cycle that was basically tau big. But then one has to do the canonical normalization now for this guy, tau phi. You can play the same game, do the exercise, and you get something now that is power law. And that's the potential, the final potential. That basically goes like 1 minus 1 over phi to the 4/3. Okay? Okay. Let's now try to see if one can do some phenomenology with this. I hope you've seen that in the cosmology course that the slow-roll inflation is controlled by two parameters, epsilon and eta. Good. See, you've seen them. So you see they are related to the flatness of the potential. Basically, when epsilon is less than 1, you are inflating. So you get an accelerating solution. And if eta is small, you accelerate for enough time. And then it's easy. You need just to compute these quantities. And they are given in terms of B, that was a number, C loop, that was our coefficient, the volume, that is also fixed and leading order, and the inflaton. Very good. Then you see that in this case, when you go to large values of phi, they become small very naturally. Then you need to compute also the number of refoldings that tells you how long inflation lasted. So then you need to integrate these. So you have your potential. So we've seen that this potential looks, roughly speaking, like this. So this is phi, then is the volume. There will be a point here that is phi end of inflation. That is the point where epsilon becomes 1. And then there could be different phi star values. Phi star can move. And then the number of refoldings tells you how many foldings of inflation the universe underwent from phi star to phi. Then this is the way you compute it. And it becomes again a function of the volume and phi star. And then, as we've seen, the inflaton undergoes quantum fluctuations. And these quantum fluctuations are the seeds for the temperature fluctuations that we see in the cosmic microwave background. People measure the amplitude of the power spectrum. Is a number which can also be written down in terms of the volume and phi star. So then you see that in these equations, for example, you can use this one. B is fixed, C loop, you can take 1 over 16 pi squared. You can write, for example, phi star in terms of the volume. You plug it back here, you get just, now phi star is written in terms of the volume. You can write the volume in terms of the number of refoldings. And this is what you find. And then you know the relation between the volume and phi star. You get also phi star in terms of the number of refoldings. And then you see that once you have a given number of refoldings, you can get two predictions. An important one is about the scalar spectral index that tells you the tilt in the power spectrum. And this is given by 1 plus 2 eta minus 6 epsilon. And again, you write it down in terms of your underlying parameters. And another important quantity, so this has been measured. This has not been measured yet. This is the tensor to scalar ratio. So it's the ratio between the amplitude of the gravity waves, of the tensor perturbations produced during inflation, and these scalar fluctuations. This is also given by 16 times epsilon, this epsilon. You substitute and you find these relations. You can write here, again, the volume and phi star in terms of the number of refoldings, and you get these predictions in terms of the number of refoldings. And even without knowing what is the required number of refoldings, you can eliminate an E and get a very nice relation between R and an S that is typical of these models. So you see, we started yesterday from string theory, and there is a lot of work. There's a big machinery, but somehow you can go down to data, which I think is pretty nice. So you want really to try to fit the data. So that's the relation. You can plot it. It's basically something like this: R versus an S. You get this line. Then you can confront that with recent data, CMB data from Planck and BICEP. BICEP is measuring the polarization of the CMB. So an important thing for us that several people most of the times underestimate is the fact that Planck and BICEP, they do not give you some universal numbers. They depend on some priors. So the standard number that is quoted, in this case, it's at 1 sigma, is if there is no extra dark radiation. So the number of effective, so this is the number of effective neutrino-like species, which in the standard model is 3, basically. This is delta NF. It means if there is extra dark radiation. But remember, we've seen before that there is always a light spectator field. So this light spectator field can be produced when the inflaton decays, will be the axion of the volume mode, and that can contribute to dark radiation. So that means that you should match the data not for delta NF equal to 0, but for the value of delta NF that you get from your model. So in the Planck paper, they gave, for example, a different estimate of NS for delta NF, which is 0.39, assuming that there is extra dark radiation. They put this number because they consider a particular model, so there is no real reason. But then you see that the spectral index shifts a bit. It gets closer to unity. And on top of that, there is only an upper bound at the moment on the primordial gravity waves. This is even at 3 sigma. It's a 68% confidence level. But then you see, to know what is the prediction, so people in general say, well, between 50 and 60 foldings. But now we want really to be precise. Once you have a model, you can compute the number of foldings. And as I will show you in the next slides, it is the post-inflationary evolution. So what happened after inflation that determines the number of foldings. So to be able to understand that, you need also to know how reheating took place. So that's something that in some models is not well understood. So here at least you can check the decay channels of all these fields. And basically we will see that you get something between 51.5 and 53 foldings, depending on some model building options. And then you get the spectral index, which is in very good agreement with data. And the tensor to scalar ratio that we find is of order 10 to minus 5. So it's pretty small in agreement with data, but still fine. So that will be a prediction for future observations. This slide is a bit technical. I don't know if we need to go through this, but it is basically checking that this potential problem with trusting effective field theory does not take place. So that you don't have this problem that when you are at the beginning of inflation, this cycle is big, you don't have any 2-cycle that shrinks down. So you are inside the killer cone. We check that for explicit Calabi-Yau realizations. But okay, this is a technicality that we can skip. Okay, so let's look at the number of refoldings from post-inflation. So the way you find the number of refoldings is by requiring that you solve the horizon problem. And that's the formula that one should use. That's why people say in general 50, 60 foldings. So the number of refoldings should be 57 plus 1/4 the log of R. In this case, R we've seen is 10 to minus 5. So you can plug it there. You will get minus 5 divided by 4 log of 2, log of 10, which is 2, roughly speaking. So this would be something like 57 minus 2. Then you have this guy here, which is the log of the ratio between the energy density at star, so at phi star, and the energy density at the end of inflation. If the potential is pretty flat, these two energy densities, which are basically given by the height of the potential here, are almost the same. So that factor is not that important because you get a log of something over the 1. The two things which are important are these ones. So these are the number of refoldings of epochs after the end of inflation, where one had matter domination because of the moduli. So here what happens is that inflation ends here, then phi goes down, starts oscillating around the minimum and dominates the energy density. But this epoch is also counted by some number of refoldings of phi oscillations around the minimum, which I'm denoting as n phi. So this will be the number of refoldings n phi of tau phi domination. So the energy density is dominated by matter in that case. Now that guy will decay and produce radiation. At a certain point, however, later on, chi in this case is the canonically normalized volume. The volume, remember I mentioned the cosmological moduli problem yesterday, that during inflation the other moduli are shifted a bit. One here can really check that the volume is fixed, it's true, but its minimum gets shifted a bit because of the dynamics that I explained yesterday. So in the late time universe, at a certain point, also the modulus start oscillating, and it gives rise to an epoch of volume domination. One has to include all this stuff. It takes a bit to compute all these things, but that's the picture, as I said. So you have inflation, and this is what happens to the volume modulus after inflation. It starts oscillating, and then it decays. It sits at late times at the minimum, and all its energy density goes into the production of hopefully standard model particles. Why did I say hopefully? Because phi now phi can be either tau phi or the volume, because there are these two epochs, can decay to standard model degrees of freedom, which can be open strings living on brace, wrapping these cycles. But there is always a decay channel that is unavoidable into the superlight axions. Remember, I mentioned these axions associated with the big cycle. These guys are gravitationally coupled. Remember, because they are coming here, they are paired up with tau, so they are gravitationally coupled, which means that they never reach thermal equilibrium with the thermal bath. They just free stream, and they are produced as relativistic at the beginning because they are very light. They just free stream till today. They are still around, and they will contribute to the number of effective neutrinos because they will behave as neutrinos. And by the way, this is also a very nice prediction because it will tell you that on top of a cosmic action, on top of a cosmic microwave background, so a background of photons everywhere in the universe, there is also a background of actions everywhere in the universe. There is a cosmic action background. So the technique is tricky because these actions are only gravitationally coupled. And one way could be to look at delta F. However, present bounds on delta F you see are pretty tight, so you cannot have too much. You can have at most something of order 0.5, a 95% confidence level, and that sets strong constraints on the decay rates here, because how much you produce will depend on the branching ratios here, which in turn depend, we will see, on basically this decay channel, because this is more model dependent, because it depends on where the standard model sits here. Remember, standard model can sit on the 7 branes or the 3 branes, and they can be wrapping this cycle, that cycle, They can be D3 branes and singularities. That changes this decay rate. But the other one is just a bulk physics feature, is always the same. So if we manage to compute this number of e-foldings, then we get the exact number of e-foldings for inflation. We can plug it back in the formulae I showed you before and get the exact prediction for the spectral index and the tensor to scalar ratio, which you see depend on the post-inflation evolution. So if you don't know what happened after the end of inflation, you're actually not able to make precise prediction for what happened during inflation. So that's an important message. Yes, very good question. But that would be a different production mechanism. Because dark matter, these guys are not dark matter, but they are dark radiation because they're relativistic. To be dark matter, they need to be non-relativistic. And there are two different production mechanisms. So this is basically the situation where you have a heavy field, phi, that is the inflaton, that would decay into two of these axions, theta B, theta B, and they are relativistic. The mechanism that you mentioned about dark matter is just the misalignment mechanism. So it's just that you have the axion potential, that is some periodic cosine-like potential. And what happens is that basically this can be useful for everyone. So this is just a symmetry, is the standard Higgs mechanism. So it is, the Higgs mechanism, you have at the beginning something like this. Then this breaks down and it goes to something like that with a Goldstone boson. That would be the axion. And so then the system goes down to some initial value. Because this is what happens in these cases. And the scale where this transition happens is given by the decay constant, F of the axion. This sets the energy where the Peccei-Quinn symmetry gets broken. You can compute it for these guys, and this becomes of order the Kaluza-Klein scale for these stringy axions. So which means that in the effective field theory, you never see this. In effective field theory, you just see the axions. It is a non-linear realization of this symmetry. Basically, it is always broken. Now, so at this point, the potential for these guys is flat, right? They experience a flat potential. And now what happens is that you have inflation. So inflation, the scale of inflation, H inflation. I didn't write it down here, but I think it's 10 to the 13 GeV, something like that. But the important thing is that this is much smaller than MKK. Well, because we are in the limit where we trust effective field theory. So, which is FA. So during inflation, we are, the axion is in this situation. So there could be different patches of our universe. Like in one patch, the axion is here. The other patch, the axion is there. The other patch, the axion is there. There are different initial values. And these are causally disconnected, because what happens is that these transitions take place before inflation. Then you have inflation, because it's a lower scale. And so these patches get just accelerated. There is an accelerated expansion. So they become, so basically the whole universe, the whole observable universe becomes only one patch. And each of them has got a different initial value for the axion. Then at a certain point, you have the non-perturbative effects for the axion get undone. And you have this potential that gets formed. And now this is the axion, let's say theta B. And then depending on what is the initial position, depending on which patch was selected, the action will start oscillating with initial amplitude that is different in different regions. And now this is just an oscillating field, similar to what this does before decay. And this behaves now as matter, and it can be dark matter. That's the picture. And by the way, different regions give rise to different predictions for the dark matter abundance. And the theory doesn't tell you which value is predicted. It just tells you that with equal probability, because this is just a flat distribution for initial conditions, you can have different values. And some of them will give too much dark matter, and there will be one of them that gives you the right value.
We just made to match our reality or something like that.
Yeah, I think there's nothing wrong with that, in the sense that there are different options. And basically, in principle, all of them can be realized in nature. But given that they are causally disconnected, once you are making observations, you can see only what is inside your patch. And the theory doesn't tell you if you are here, there, or that. But it tells you that, for example, this one could give dark matter reproduction. This could be dark matter reproduction. Then you see if there is at least one that matches data, it means that we're there. I think there is nothing wrong with that. It might not be generic, so one might not like that, but there is nothing wrong.
Is this also like in simple models of inflation? You assume that the yield of the market stay right, and the it is a this uses a justification provide this.
Mm-hmm. No, but that's the axiom. That is the axiom. Yeah, I mean the scalar field is the one responsible for inflation. But you see that this is a field when you can have two different production mechanisms for the same field. So this is called misalignment. Misalignment. In this case, it is dark matter. So this is dark matter, and actually it has a name which is called fuzzy dark matter, because this guy is ultralight. But it can also be produced from the decay of a heavy field, and this will be relativistic, and this is dark, now not matter, but dark radiation. So you have these two contributions. Yes, yeah. This, I mean, people have, I mentioned before, you see there are bounds. People measure this. Of course, if you increase, you see intuitively that if you increase the amount of radiation in the universe, you change the expansion rate, which is constrained by observations, and then you can get down to this. But there is not that much space. Like in the standard model, so you should see this as the standard model value plus delta NF. The standard model value basically is 3 because of the 3 neutrinos. Now, this is not an integer because it's defined in terms of branching ratios.
So, I can say scalar as the when I can say scalar is
A what? A dilaton. No, we've seen that there is a dilaton, okay, which is the field that is whose vacuum expectation value gives you the string coupling, right? But this field is not a good inflaton candidate, because we've seen that this field is the one that receives a potential first. So it's one of the heaviest fields. So because you should think about the potential as the potential, which is a multi-field potential. There are some directions which are steeper and other directions which are flatter. And if you start from an arbitrary initial condition, the system will first evolve along the steepest direction and then along the lightest direction. So the dilaton in this scenario is one of the heaviest modes. So it would then, during inflation, it is just a heavy spectator, sits at the minimum and does nothing, basically. More questions? Standard model realization. So we want now to compute the number of refoldings, understand how reheating works. That depends on where the standard model is. Now, let's say that the standard model is on the 7 branes. Now there are different options, but there can be, so this is a bit technical now, but I will try to make it as simple as possible. So it could be that this guy, I can consider some standard model D7 wrapping tau small. Because one thing that you should remember is that g to the -2 goes like tau. Remember that? Now we know what g to the -2 is for the standard model. So these are the couplings of the standard model. So this is for the 10, 100, not more than that, right? Let's say for the 10. So this means that I cannot put the standard model on the big cycle. Because if I put on the big cycle, I wouldn't be able to reproduce the standard model gauge coupling. Right? The gauge coupling would be super small, right? Because the tau big is huge. So then it has to be either tau phi or tau s. If I do this here, there is a problem because of the tension between non-perturbative effects and chirality. So basically what happens if you do that, you have that these non-perturbative effects, which I don't know why there are two white slides now, that were used here as a function of TS, the prefactor AS would depend on standard model fields. So this will depend on, let's say, phi, with phi as standard model field. And if these fields get a 0 vacuum expectation value at high energies, this AS would become 0. So you would kill these non-perturbative effects, but you want to have them, right? Because you need them to stabilize the volume. So this means that that option is not the best one to realize the standard model. So we should not have that the standard model, the 7 branes are here. Now, why not putting them here, right? The standard model D7, because that's the inflaton. And if I have that the standard model is there, there is a direct enhanced coupling because of the locality in the extra dimension between tau phi and the standard model. However, also this case will not work because one generates phi Heliopoulos terms. I don't know if you've seen them, but phi Heliopoulos terms are a contribution to the action or to the potential that you have in supersymmetry associated to U1 abelian symmetries, which in this case are inflaton dependent, so they are moduli dependent. So these phi Heliopoulos terms would give you an extra contribution to the potential that depends on the inflaton and would make it too heavy. So that is something that one should avoid because then you ruin the flatness. So also this possibility does not work. Then what happens is that you need to add other cycles. So the model might start looking a bit baroque, but actually I would say that it is not, because we are trying to put together many things, right? We are trying to put together inflation, reheating, the construction of the standard model at the same time. So it is not so strange to expect that you need to have some features in your model to be able to reproduce all this stuff. And basically, you introduce tau standard model. You see all these things come with a minus sign, so they are all blow up modes. And there is another tau, which is tau int for intersection. So you should think of these as, again, other two holes which intersect. So let's say tau standard model, tau intersection. And now I can put the standard model with the 7 branes wrapping this cycle. And now what happens is the following. So D terms are extra contributions to the scalar potential that you have in supersymmetry. So these are leading order contributions to the scalar potential. So you need to set these D terms to 0 to get a leading order supersymmetric solution. These are these Fayet-Iliopoulos terms. They depend on the moduli, so setting them equal to 0 gives you a relation between the moduli, and it would basically stabilize tau standard model in terms of tau int intersection, or vice versa, whatever, leaving a flat direction. So now, if the model is such that lambda is 0, so you don't have this term, so you have just tau standard model, so that would be a situation where you don't have this cycle. And then the Fi term equal to 0 would just send tau standard model to 0. So this will shrink down to a singularity. And in that case, you can have basically a situation where this cycle now, this tau standard model, because of the term stabilization, goes to 0. So tau standard model goes to 0, so you get a singularity. And there you can have D3 branes. And D3 branes and singularities, it's a well-known area of research that people explore to get chiral matter. So here there are also open string. You can get chiral matter, and then the standard model can live on these D3 branes. So that's a possibility. The second possibility, so that would be a situation where you don't need tau intersection. You just have tau standard model. But if tau intersection is there and lambda is different from 0, then you see I'm still left over with one flat direction, which can be again stabilized by loops. And one can find that these are stabilized to something of order 10, and then you can reproduce the standard model gauge coupling. Whereas in the situation of the D3 branes and singularities, remember that the gauge coupling was given by the dilaton, by the string coupling. And if that is of order the standard model couplings, this can work. Okay, so there are these two possibilities. So the standard model can be either on the 3 branes at the singularity, or on the 7 branes on an additional cycle. Now, for simplicity, let me ignore this tau intersection. So let's say that there is some tau. This tau intersection was just needed for stabilization. But let's say that there is a third cycle, tau standard model, where the standard model is 7 branes sit, which can also be shrinking to 0 size, and then you have D3 branes here. So these are the possibilities. And now in these scenarios, one can start computing the decay rates to get reheating to the standard model. First of all, you have to compute the mass. You need to compute the mass of these fields, of the canonically normalized fields. So you need to expand the theory around the minimum, because now the inflaton has reached the minimum. You expand the theory there, and you canonically normalize, you compute the masses, and interestingly, you find that you see the big quantity is the volume. So look at powers of the volume. The inflaton that during inflation was lighter than the volume. Remember here, when you are in this region, the inflaton is lighter than the volume because this potential is very flat. But now we are computing things around the minimum. Around the minimum, the inflaton, the canonically normalized inflaton, becomes heavier than the volume because its mass goes like 1 over the volume, whereas the mass of the canonically normalized volume chi is 1 over the volume to the 3/8. There is a simple way to understand that. Maybe let me come here. Because is this the best? Well, no. Maybe here it's better. So there is a very intuitive and quick way to understand that. Of course, one has to compute the mass matrix, do the canonical normalization, and so on. But remember that you had a potential V that was going like, there were contributions like 1 over volume cubed. Then there were contributions like e to the minus tau phi divided by volume squared. And then there were also e to the minus 2 tau phi divided by the volume. Now, the mass squared is given, roughly speaking, by the second derivative of the, let's say, the one of tau big, where the volume is tau big to the 3/2, we've seen. So this goes like the second derivative with respect to tau big. You need to look at the Hessian. It's the matrix of second derivatives. But this would be true for the canonically unnormalized guy. Now you need to canonically normalize, and then you get the inverse scalar metric tau big. And we've seen that this scalar metric is given by the second derivative of the Kähler potential, which is minus 3 log of tau big. So then you have k tau big goes like 1 over tau big squared. You take the second derivative. So now k to the minus 1 tau big goes like tau big squared in the numerator. So this quantity goes like tau big squared in the numerator. It is just this potential with the second derivative. So roughly speaking, this will go like the potential itself times 1 over tau big squared, right? Because you take two derivatives. So these two simplify, then you expect that this goes like 1 over volume cubed. And in fact, that would be the mass. Now, the canonically normalized tau big is called chi in that slide. And in fact, you see that the mass of chi squared goes like volume cubed. Now I'm ignoring these square roots. If you try to do it with, instead, there was minus tau phi to the 3/2. You try to do it with this. Now, let's see. So the Kähler potential is minus 2 log of the volume. So when you do k tau small, you get something that goes like minus 1 over the volume. Let's just look at the scaling. I don't care about the signs. And then times the derivative of the volume with respect to tau phi. So you get some square root of tau phi, right? Just by taking the derivative. Now you take the second derivative. Sorry, tau phi, not tau s. You take the second derivative and you get something like 1 over the volume tau phi square root in the denominator. Okay, then let's apply that formula. You have that the mass squared of tau phi now becomes k to the minus 1. K to the minus 1, I need to take the inverse. Of course, one has to do it properly with this matrix, but I'm just now interested at the scaling. So this scales like 1 over the volume, because this is not a big factor. So now we'll have a volume in the numerator, because I need to take the inverse, times the second derivative of the volume with respect to tau phi. But when you take the derivative of an exponential, you get the exponential itself. And each of these terms in the minimum goes like 1 over volume cubed. So the second derivative will go like 1 over volume cubed, right? So then this guy goes like 1 over volume squared. So which means that now the canonically normalized inflaton is phi, that the mass should go like 1 over the volume, and it is this result here, 1 over the volume. So intuitively you see where they come from. Now let's look at the volume first. What can the volume decay to? So the volume can decay to its corresponding axions, because we've seen that T big is tau big plus I theta big, and this is the guy whose mass is basically 0. because it is exponentially suppressed by the huge volume. So tau big, which is chi, can decay into theta big, theta big. It's easy to compute it. One can, at least let me tell you this, and then you can compute all the other as an exercise. This comes from the kinetic terms. Remember that the kinetic terms are the second derivative of k with respect t big, t bar, big bar. And then you have d mu, t big, d mu, t bar, big bar. Now I write t big in that way as tau big plus I theta big. So then you see that this will be the second derivative, big big, which is now computed at the minimum, times d mu tau big, d mu tau big. But then I have also plus k big big evaluated at the minimum times d mu theta big, d mu theta big. Right? And we've seen that this second derivative, I just computed it before, goes like 1 over tau big squared. So you see that this guy is basically, when this is a vacuum expectation value, is the kinetic term for theta big. When I expand it around the vacuum, I get instead the coupling between tau big and theta big. So from this, you can work out these couplings. So now you know the mass, you know the coupling, and you get the decay width. Other possibilities are, is there a question, guys? Thank you. So the other possibility is that there is a decay into Higgs fields. Now, one can compute it. Well, basically, this depends on the fact that the standard model is on D7 brace or on D3 brace. So these two options. Because basically what happens is that there is a different scale of supersymmetry breaking. So, and the Higgses get, of course, contribution from supersymmetry breaking. So in this situation, one has that the mass of the SUSY particles is of order the mass of the gravitinum, which goes like 1 over the volume. So this means that chi, whose mass goes like 1 over the volume to the 3/2, is lighter because of the volume powers than the supersymmetric particles. So which means that it cannot decay to any supersymmetric particle. It can just decay to the standard model Higgs. And this is what I denoted as little h. So here I have a decay, in this case of chi, into theta big, but it can also decay into the standard model Higgs. In this other situation, instead, there is sequestering, which I mentioned already this morning. So m SUSY, in this case, goes like 1 over volume squared. One has to compute that, but believe me. And now this is smaller than the mass of chi. So chi can decay into, so that will be a situation where it decays into theta b, but now it decays into minimal supersymmetric standard model Higgses. This will be X up and X down. So there are different decay channels. And they can be computed and they are there. What happens to the infraton? Because we need also to compute the decay rates of the infraton. So tau phi. Now it depends. So the infraton cannot be wrapped by the standard model D7, as we've already seen, because one would have problems with this Fayet-Lioplus term that would ruin the flatness of inflation. But it can be wrapped by some hidden sector D7. So there is nothing wrong with having some hidden D7. Of course, let me say that to understand this brain setup, one should have an explicit Calabi-Yau model where you know the action of the oriented involution. You can check tidal cancellation, the contribution of the fluxes, and so on, to see which configuration is consistent or not. But now I'm just exploring all the possibilities from the phenomenological point of view. And actually, we'll find that in the end, the final predictions do not change that much. So in this situation, what happens is that this guy decays into photons that are in the hidden sector. Now, this decay comes from this, right? Because you also here intuitively, you can see that there is a coupling from the fact that g to the minus 2 is tau. So if I have 1 over g squared f mu nu f mu nu, so I have a term like this becomes tau f mu nu f mu nu, and this is a coupling between tau and two photons. That would be the situation where here the canonically normalized tau that I called phi. So that would be a situation where phi decays into a pair of gamma hidden, gamma hidden. And that's it. The main decay channel is just that one. However, the second possibility is that this is not wrapped by any D7, by any hidden D7. So what happens is that in this second situation, tau phi would decay into the volume because it's lighter. So you have that phi decays into chi chi, but it can also decay into theta b, into the corresponding axions. Then if the standard model is on the 7 branes, like this, chi in turn would decay into again theta b, so more contributions to dark radiation, but to Higgses as well. So that's how you reheat the standard model, always via Higgses. But if the standard model is on the 3 branes, you have instead this other decay channel. On top of that, the last possibility, if the standard model is on the 7 branes, there is also the possibility that phi, on top of decaying into chi and theta b, decays also into this guy, into this tau standard model. One has to check all these decay channels. It decays also so into a pair of these guys. It can decay also into photons or gauge bosons in the standard model, gamma gamma, and it can decay also directly to the QCD axion, which is on the standard model branes. So one has to carefully check all these decay channels. And for example, this tau standard model in turn decays into gamma gamma and the QCD axion. So you have to compute it, and then you see that in this case, this will be dark radiation, this will be dark radiation. All the other modes are standard model fields. And well, this will also be dark radiation, by the way, because the QCD axion is light, but all the other channels lead into the standard model. So this is how you would reheat. Okay, just a few simple slides left over where there are pictures and results. So now you apply this general study to all the possible situations. So let's consider a situation where the standard model is on the 7 branes and the inflaton is wrapped by the D7, by hidden sector D7 branes. So you have that inflation, at the beginning of inflation, tau phi is big, then it becomes small. It's wrapped by hidden D7, and the standard model sits on this tau standard model. So now what happens is that you have inflation. Now after the end of inflation, immediately the inflaton decays into the hidden sector and produces this hidden gamma gamma. Very quickly, there's only one enfolding. So we computed all this. The universe becomes radiation dominated because these gammas are radiation, but it's all hidden radiation. It's all dark radiation. That's very bad. However, later on, the volume starts dominating the energy density. So the blue means matter domination and yellow radiation domination. There are 3 foldings of volume modulus domination, and then it decays back into Higgses. So it would be this situation here, and it reproduces the standard model. And then you have the standard Big Bang picture from here on, matter domination, dark energy. And the total number of foldings becomes 53 of inflation. So you can really compute it exactly. You can plug it back in the formula we've seen before, and you get nice predictions for the spectral index, the tensor to scalar ratio, the reheating temperature. And in this case, basically, given that the last decay is mainly into Higgses, you don't produce any dark radiation. So one has to match Planck data where delta NF is 0. And this match is pretty good. And that's the prediction for the tensor to scalar ratio. One can try the other possibility where now there is nothing wrapped around the inflaton. And you see the post-inflation evolution is different, because now the inflaton, given that it's not wrapped by any hidden sector, you don't have a quick decay channel into hidden sector gauge bosons. So the epoch of inflaton domination lasts longer, up to the point where the inflaton can now decay into gamma gamma and theta b via all these decay channels. And given that this epoch is so long, you don't have any volume modulus domination, because basically the volume mode doesn't have enough time to dominate the energy density. It decays too quickly because there is this long epoch of inflaton domination. However, now when phi decays, it decays also into axions, and we computed exactly, that's another prediction. In this model, delta NF is 0.14. In this scenario, the number of refoldings becomes 52. It's not 53, but it's pretty similar. And the predictions for NS and R are rather similar. The reheating temperature is a bit higher, though. Here is 10 to the 12 GeV. Previously was 10 to the 10 GeV, mainly because this reheating temperature was given by the decay of the volume. Whereas in this second scenario, you don't have any late time volume domination, so it just comes from the inflaton, and it's a bit higher. Then one can try the other possibilities where the standard model is on the 3 brainset singularities. You can play the same game using all these decay channels. You have again inflaton domination, volume domination. And in this case, you see the predictions for NS and R are pretty stable. Also, the number of refoldings is almost the same. What changes is delta NF. Here you produce more from the decay, again, of chi into axions. And the standard mod, the MSSM Higgses, would instead reheat into the visible sector. And that's the case where the inflaton is wrapped by some hidden, D7. We checked also the case where the standard model is on D3s, the inflaton is not wrapped by any hidden D7. The predictions are very similar. And that's it. So we found that the predictions are very robust. Somehow, in terms of potential possibilities for the standard model construction. And also, there's a model, I think, where you can really go from inflation all the way down to reheating. You see how the standard model degrees of freedom are produced. You see what happens after the end of inflation. You can get a prediction for the cosmological observables during inflation, but then you can get extra predictions, for example, for dark radiation and for dark matter as well. I didn't talk that much about dark matter. I mentioned the misalignment, so that's a possibility. There are other possibilities, for example, from the neutralino, the supersymmetric particles. And it's a model you can test. You can try to confront it with data, so that at least you could see an example where you go all the way down from string theory to observations. And basically here, this is just the summary. These are the predictions considering different models for the standard model construction. So you see NS is pretty stable in this region. R is always of order 2 times 10 to minus 5. Also, the number of refoldings is around 52, 53. And delta NF is generically different from 0, which is something I think pretty interesting because it's a kind of prediction. So every time you want to trust your effective field theory, you go to large volumes. Exponential suppressions from non-perturbative effects give very light masses for the axions. There are moduli which dominate the energy density and tend to decay into these axions. So you tend to have some delta NF, which is different from 0. And I think this is a feature that is not just of this model, but of more generic string scenarios. So I think I'm done. I finished 10 minutes earlier. So if you have questions, we could use these 10 minutes. Or if you're tired,